but there's always things I've got to do. So, if you want to come a little early, won't stay a little late, that's fine. We'll do that. Just looking at the basic formulas, it has all the equations on it that we've got. So we've got the first test was over waves. Waves in general and then sound waves in particular. So you had the speed is frequency times wavelength, that equation. Generalized, what they call a sinusoidal wave or something like that, what would be the displacement, say in the y direction, if the wave is going in the xy plane up and down as it travels, say the x direction. That y coordinate would be the maximum amplitude times the sine of the kx minus omega t, where the k is the 2 pi divided by the wavelength, and the omega is the 2 pi times the frequency of it. And if you take the omega and divide by the k, then you end up with the f lambda, which would bring you the speed of it. So you had that equation. Or if you took the derivative of the y, you would have not the wave speed, which is the omega divided by the k, or the f lambda, but that transverse wave, the speed of the wave. So as the particles are going up and down, how fast are they moving at a particular x and t as the y changes with respect to time. So you had those equations. For the string, speed of the wave on the string was the square root of the tension divided by that mass per unit length of the string. We had that. If it was a sound wave, that was the other wave speed equation we had. We had the speed of the sound wave was the 331 meters per second, then times that square root of 1 plus the Celsius temperature over 273. If you're using Kelvin, it's just the square root of T over 273. So leave off the 1 plus if you want to use Kelvin. You got your formula sheet, all I've got is that one, that form of it. But temperature in that equation is in Celsius for that. So we got into sound waves was most of it after that, as well as you have strings and then sound waves. Sorry. The intensity, power over the 4 pi r squared, where the r is the distance from the source. That's assuming it's a point source and these waves are traveling out spherically. So how intense is it? Watts per square meter. Drops off is 1 over r squared. The further away you get, the less intense the sound becomes. The loudness. How loud is that sound? That's the decibel. And that's the 10 times the base 10 log of intensity over 10 to the negative 12. So that equation. So anything dealing with loudness and or intensity, we've got these two equations we can work with. If you can have these standing waves. Okay, so think of that second lap we did with the standing waves on the string. Or was that the first lap? Anyway, whichever lap it was. For the string, the resonant frequencies, what frequencies are going to give you these standing waves? For the n times that, or n over 2L times that square root of tension over mass per unit length, where the n is an integer value, so 1, 2, 3, 4, 5, etc. Remember that looking at that standing wave on the string, that n equal 1 or 2 or 3, that's how many of those half wavelength segments you had along the string. So it's just one segment, that was n equal 1. And the two segments going along, that's n equal 2. Three segments, that was n equal 3. That was for the string. For a open path, like your flute or something like that, the resonant frequencies were the n times the speed over 2L. Again, n is an integer. It's the speed of the sound wave going in the path. If it was a closed path, then the resonant frequencies were NV, or excuse me, not 2V, NV over 2L. And for the closed path, it was NV over 4L, and the n's were odd integers in that case. So you got a quarter of a wavelength inside the pipe, or in 3/4, or 5/4, or 7/4, as opposed to just the half or the half of a wavelength, or one wavelength, or 1.5, or 2, or 2.5, or 3. These were the quarter wavelength type segments within that, because closed pipe, the closed end, you had to have a node for the standing wave at that end, and for the open end, you had to have an antinode. So from a node to an antinode is a quarter of a wavelength, and then it depends on how many other half wavelengths you have. And so those were the standing waves in various pipes, or various pipes or strings. Doppler shift. Okay, so if you've got a source and an observer that are moving relative to each other, either one could be moving and one stationary, or they could both be moving, but they're either getting closer together or further apart as they move. Then the observed frequency was the source frequency, and you had the speed of the sound wave in air. So it could be, if you're given a temperature, you can use this kind of speed. Otherwise, I would tell you use 345 meters per second. The problem would say something about what to use for that speed. In fact, I'll probably be one of those things I'll put on the board here to test. Speed of sound in air, 345 meters per second. So use that unless you're told the temperature, and then you use this equation to find the speed. Speed of the sound wave plus or minus the speed of the observer divided by the speed of the wave minus or plus the speed of the source. And the plus and minus, if the observer is going toward the location of the source, then we use the plus sign. The observer is going away from where the source is located, then we use the minus sign. Just which way, think the vector direction for that. So they could both be moving, but if the observer is going towards, it is the source that's the observer. The observer is going toward the source, that's the plus. If it's going away from the source, that's the minus. Whether they're getting closer together or further apart doesn't matter. It's which way is that vector from the velocity pointing. And then same thing for the source. If the source is going toward the observer, use the minus sign. If it's going away from the observer, use the plus sign. We had that for the Doppler shift equation. We had various kinds of problems we worked with that. The beat frequency. Beats, the beat frequency, absolute value of the difference of two frequencies being played simultaneously. Okay, so you're hearing these two frequencies. The difference of those two is the beat frequency. Remember, that's that variation in the loudness of the sound. As the frequency gets louder, as they get more constructive interference, it gets softer as they get more destructive interference over time. So you have that equation for beats. And as far as chapters 15 and 16, those were our equations. So that was what we covered on that first test that we took. Second test, we got into electricity. Okay, so chapters 21 through, like 26. So the electric force, one charge puts on another charge. Coulomb's constant, K, it's that 9 10 to the 9th number, times the product of the two charges divided by the distance between the two charges squared. Got coulombs times coulombs divided by meters squared gives us force in those newtons. Electric field. Force per unit charge, or for a point charge, would be the KQ over R squared. Electric field always points away from a positive charge, it points toward a negative charge. Force and electric field are both vectors. So you got to think in terms of direction that they're going as well as how much they are. This would give you how much they are. In this case, the Q's, if they happen to be negative, put them into the equation as positive. So you're ending up with just a number for the force or the electric field strength, but then you look to see what direction they are. Because if there's more than one force or more than one electric field always calculated at a point in space. If there's more than one, then you've got to add them together vectorially, not just the magnitudes. So force and electric field, which was basically what we had in chapter 21. Chapter 22 on Gauss's law, we skipped that totally, didn't do anything in that. Chapter 23 got into voltages and potential energy differences. And so the change in the electric potential energy, as opposed to like gravitational, is the charge times the difference in the voltages from one point in space to another point. You got joules is coulombs times volts. We did use that in a thing like if you have your proton, you're going to put it in a voltage. It's going to go from pushed away from the positive charge and toward the negative side of the voltage, and it's going to accelerate. And we said the change in the potential energy was equal to the change in the kinetic energy. So you had the Q times the voltage is equal to the 1/2 mv squared. So change in potential energy, and starting from 0, change in kinetic energy. Go from 0 to the final kinetic energy. Or from initial being 1/2 mv squared, and the final being 0. So you're either speeding it up from 0 to something, or slowing it down from something down to 0 speed. So you had those kinds of problems where we did that. It came back in the relativity. So remember I said that if you were doing that, but it's moving at some relativistic speed, greater than about 5% the speed of light, then I can't use this for kinetic energy anymore. I have to use that relativistic kinetic energy that we talked about in doing this type of equation. So we have that. If it's point charges, the potential energy due to a group of point charges is a summation of the K times the product of the two charges divided by the distance between those two charges. Groups of two. This is not a vector, it's a scalar. So if you got negative charges, put them in as negative numbers when you're doing this one. And again, this is just you're effectively looking at how many different groups of two charges do you have. If you've only got two charges, there's one term. If you've got three charges, you got 1, 2, 3 terms for that. If you had 4 charges, there'd be 6 terms. So 1 and 2, 2 and 3, 3 and 4, 4 and 1, and then 1 and 3 and 2 and 4. And that definitely wouldn't give you anything more than that, probably not even that. But it's just how many groups of two do you have? That's the potential energy of that group of charges. you're looking for a potential or a voltage, electric potential. Remember, this is electric force, electric field, electric potential energy, and then the V is the electric potential, without the word energy. Well, that's a summation of the K times each of the charges divided by the distance that charge is away from whatever point you're calculating the voltage for. And again, V is calculated at a point in space. And you just, again, that's a scalar, so if the charge is negative, put it in as negative. That's summation, which was all of chapter 23. 24 started getting into circuits. We had capacitance. Capacitance ratio of charge on the capacitor, the two sides divided by the voltage difference between those two sides. But remember, C doesn't depend on Q and V. It's just related to them that way. Just like speed is frequency times wavelength for a wave, speed doesn't depend on the frequency of the wavelength. It depends on properties of the medium, like the tension of the mass being the length of the string or the temperature of the air for the sound wave. If it's a parallel plate capacitor, that capacitance was the dielectric constant, what's in between the plates. That, again, you'd be given that number, you're using it. The epsilon naught constant, and if you need that, I'd put it on the board. That's that 8.85 10 negative 12 number, times the area of the plates divided by the distance between the plates. How far apart are those two plates separated? That's the D. What's the area of the plates? That's specifically for a parallel plate capacitor. Energy stored when you got a charge on a capacitor. How much energy is stored in that electric field? That's 1/2 of Q times V, but Q is C times V, so that could be written as 1/2 CV squared, or V is Q over C, so you could write that as 1/2 Q squared divided by C. All of those are equivalent forms, so if you do know two of those, Q, V, and C, you can find the energy by just using the appropriate form for that. And 24 and 25 were, and 26 were everything dealing with capacitors and resistors in DC circuits. And so instead of trying to put them separate, we're going to put them all together in a minute here. So that capacitor is 24. 25 got into current. So how much charge per unit time is going past a point? Or if you've got current, Q as a function of time, you can write that as a dQ dt. You do a derivative to find then what's the current at a particular time, as opposed to what's like an average current between two times. You know how much charge and how much time it takes to go from one point to another. So, had that resistance or voltage was current times resistance, Ohm's law. But then resistance was the resistivity, so that's a material number, times the length and divided by the cross-sectional area. Think of the wire, how long is the wire, and then what's that area of the cross-section as you're going down the wire. That's the resistance. The resistivity as a function of temperature. The resistivity, the rho naught is at 20 degrees Celsius, and then times your 1 plus the temperature coefficient number, the alpha, and then T minus 20. Now, probably you're not going to need that temperature-dependent equation there, but remember, it's on the formula sheet, so I'll mention it. Had that. And then, let's see. power. You got current going through a resistor. Power is current times voltage across the resistor, or it's current squared times resistance, or it's voltage squared divided by resistance. You have those relationships. And then in series and parallel circuits, and so if they're in series, the charge on capacitors is the same if they're in series. If it's current going through a resistor, since current is just moving charge, current is the same in all resistors that are in parallel with, or excuse me, in series with each other. It's the same current. If they're in parallel, total charge is the sum of the charges on each of the parallel branches. Of course, in a branch you could have things in series also. But it's just the sum of everything in this branch plus all the charge on that capacitors in that branch. Same thing for current. Total current going through parallel branches is the sum of the currents going through each of the parallel branches. We only list two, but again, it could be more than two. There are three in parallel. Current 1 plus current 2 plus current 3 give you the total current. Voltages, when they're in series, the total voltage is the sum of the individual voltages across each of the things that are in series. These could be capacitors or resistors. When they're in parallel, the voltage on each of the parallel parts is equal, and it's equal to the total voltage across the whole parallel circuit there. And then what's the equivalent capacitance? So in series, you had 1 over the equivalent is equal to the 1 over the first one plus 1 over the second one plus dot, 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 everything you've got. For parallel capacitors, total capacitance was the sum of the individual capacitances in each of the parallel branches. For resistors in series, you did the summation. So like two resistors in series, you add the first one plus the second one, and that gives you your total resistance for those two in series. If they're in parallel, it's 1 over the equivalent is equal to 1 over the resistance of the first branch plus 1 over the resistance of the second branch. And again, you know how many branches you've got. Just keep adding terms. So that's all those things when you've got either capacitors and or capacitors or resistors in either series or parallel. If you've got multiple series and parallel, first thing you do is find the total equivalent capacitance or resistance, depending on which one you're working with. Then, knowing the total capacitance, this, you could use this to find the total charge if you say what the battery is connected to. Or if you had resistors in parallel series combination, use these equations to find your total resistance, and then use V is I times R to find the total current going through it. And again, I would stop it, if I give you one like that, I would stop at just that point. I wouldn't say, you know, how much current's going through each individual resistor, or what's the voltage across each individual capacitor, or anything like that. Okay. All of these, if you've got one battery, capacitors in series and or parallel, resistors in series and or parallel, but only a single battery. If you've got a resistor and a capacitor, the RC circuits, so when you're charging a capacitor, there's no charge on it to start with, you connect it to the battery, so it's a battery, a resistor, and a capacitor. Then the charge on the capacitor is the capacitance times the voltage. The voltage is the battery voltage. 1 minus V negative T over RC equation. Voltage on the capacitor then would just be the battery voltage times the 1 minus E negative T over RC. Current going through your resistor as a function of time would be the V over the R times the E to the negative T over RC, and the voltage on the resistor would be the V times the E negative T over RC. So that's if you've got one battery again, but you've got both a capacitor and a resistor, and they are in series for this. I wouldn't have RC when they're in parallel. So we've got that. And then the last thing we looked at all of these chapters was Kirchhoff. Oh, there's Kirchhoff. Okay. If you've got multiple batteries in parallel, then you've got to use Kirchhoff's laws. And so you've got the Kirchhoff's current law that says the sum of the currents going into a point has to equal the sum of the currents coming out of a point. And that's just like resistors in parallel. All right, yeah. What goes in has to equal what comes out of that branching point. And then the KVL equations, sum of the voltage changes around a closed loop. So you work your way around the circuit, start at some point. When you get back to where you started, the sum of those voltage changes has to be 0. And when is it positive, when is it negative? If you go across a battery, you're going from the negative side of the battery to the positive side as you go around this loop. That's a plus voltage. If you go from the positive to the negative, that's a negative voltage. Write that down. If you're going, you got a resistor, and the current's going a certain direction. If you're going the same direction as the current, as you work your way around the loop, it's a minus I times R voltage change. If you're going against the current, it's a plus I times R voltage change. Those were Kirchhoff's laws. And again, if you had like that typical Kirchhoff circuit, resistor, battery, another parallel resistor for the battery, V2, and then a third parallel branch, and some sort of a battery there. And so as you've got 2 points where wires are coming together, so you pick one of those 2 points. You know, if I give you this, I can tell you which point to pick. And you write currents going in equals currents coming out. So maybe you had current 1 going this way, current 2 going that way, and then current 3 this way. And so KCL at this point would be I2 equals I1 plus I3. That's the way I've got it drawn. And then you'd have to do KVL, and you'd go around a loop, pick 2 of the 3 loops, got the KVL equations for that.